Look at a well-designed system, and you will find strict boundaries, physical divisions separating where data is stored from the mechanisms that operate on it. If you write object-oriented code in Java or C++, the language automatically identifies which object instance you are working with, using an implicit this pointer. But in Python, developers must explicitly declare a parameter called self in every single method signature. It creates a strange paradox. Python behaves like a modern object-oriented language, yet it requires the manual injection of the object into its own methods. The secret is that Python does not treat the word self as a reserved keyword, and it is not an automatic system variable. You can name this parameter me, and as you can see in this output, the code executes perfectly. But if you remove the parameter entirely, the interpreter pushes back. This terminal traceback shows a type error. A type error is an exception raised when an operation is applied to an object of inappropriate type, or in this case, an incorrect signature. The error states the function takes 0 positional arguments, but 1 was given. You didn't provide an argument, the interpreter did. This error proves that behind the scenes, Python is quietly passing a hidden argument the moment the method is called. Self is a normal parameter catching that hidden argument. It acts as a window into Python's dynamic binding system. To see exactly what is being passed, we need to bypass the syntax and map the raw memory layout. When an application runs, it allocates physical memory spaces to different structural concepts to keep operations organized. In Python, objects obey a strict architectural rule, the physical separation of data and behavior. Python allocates a type object block containing a dictionary. This stores all function objects, like our bark method. Instantiating creates a separate instance block. It contains an empty dictionary for data, holding 0 functions, and an OB type pointer routing back to the class repository. Because instances do not contain their own methods, Python must execute a specific bridging process to connect the isolated instance data to the class function. The millisecond a method call is triggered in your code, the interpreter initiates an exact sequence to locate that function. Attribute lookup deploys a search probe, checking the instance dictionary for bark. It fails, as behavior isn't stored here. Tracing the OB type pointer up to the class block, it locates the target. But this raw, unbound code doesn't know which instance triggered it. Attribute lookup merely retrieves the logic. It leaves a mechanical gap in how that generic function gains access to your specific instance's data. To bridge that mechanical gap, we have to look inside the internal structure of the function object itself. All Python functions contain a hidden mechanism embedded with them called the Descriptor protocol. Accessing a function via an instance triggers its internal .get method. It receives the instance pointer, d, and the class type, dog. This creates a bound method containing a .func pointer to the original logic and a .self pointer routing back to the instance data. The Descriptor protocol is the true bridge, fusing disconnected memory spaces, the data and the behavior, into a single executable context. Standard dot notation syntax serves as a convenient interface for the underlying binding process. During execution, the syntax d.bark is translated to Dog.bark d. The bound method inserts the instance pointer as the first explicit argument. For a modifying method like setName, this argument is the handle needed to inject new key-value pairs into the object's local state. Self is simply the developer-facing name for this explicitly passed dynamic memory handle. We can validate this exact memory model by examining the foundational C structure of the CPython interpreter itself. When calling a method, tp-getAttribute initiates lookup in C. Step 2 scans up to type.tpdict. In Step 3, the Descriptor protocol intercepts the raw function. Step 4 creates the bound method object, and Step 5 calls it, passing the instance as the first argument. This uncompromising mechanical 5-step sequence is the reality executing underneath every single method call you write. Now that the underlying mechanics have been exposed, we can step back to a high-level architectural perspective. This animated diagram maps out a clean relational matrix of Python's object model. The object holds data. The type holds functions. The Descriptor protocol acts as the runtime mechanism bridging these separate domains, and self is the reference to that specific object. Because binding is dynamic rather than hard-coded into the language, developers can intercept and manipulate the lookup process directly. Mapping the mechanics of self provides the structural insight necessary to implement advanced features like custom decorators and metaclasses.